Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start today's lecture. First of all, still thanks a lot for your coming. And first thing I need to talk about is some typo in my handwritten notes. So sorry about that, I think in my previous lecture. So in my previous lecture, in order to perform the dropping deviance test, we need to obtain the deviance of the full model and also the deviance of the reduced model. And so the mistake is about which one is the deviance of the full model and which one is the deviance of the reduced model. Yeah, I think that's here. And the answer here is that the deviance for the full model with more variables, because usually more variables will lead to a smaller deviance. So the smaller one is the deviance of the full model, which is the residual deviance, which is the residual deviance on the previous page. So this residual deviance is actually the deviance of the full model. And the larger deviance is the deviance of the reduced model. And here, because our reduced model is the model with the intercept only, so the reduced model, so here, the reduced model is here with the intercept only. Because this model has no explanatory variables, so it is called a non-model. You can consider in this way. So the deviance is called the non-deviance. So the deviance here, 15.433 here, is actually the deviance of the reduced model. So it is the deviance of the reduced model. And 2.471 is the deviance of the full model. And so it is the deviance of the full model. So how can I annotate it? So maybe just say it is the deviance computed by fit. So fit is the output of the full model. So by doing that, we can perform this dropping deviance test. So what's dropping deviance test? Dropping deviance test basically tests whether or not one or several coefficients are equal to 0. So that's the dropping deviance test. And what you need to understand here is that you need to compare, it's not page 15, sorry, it's page 13, a lot of mistake, sorry, on page 13. So you need to compare page 14 and compare page 13 and find the same quantities, the 15.433 and 2.471. So these two quantities also appear on page 14. So you need to understand which one is the deviance of the full model and which one is the deviance of the reduced model. And by using this kind of output, non-deviance and the residual deviance, you need to compute the dropping deviance test statistic, and also you need to use the test statistic to perform the chi-square test, the dropping deviance chi-square test. So that's the requirement. And also, I think a very similar question is in the question 1 of your assignment 2. So any questions about the dropping deviance test? So basically, I make a mistake, and do not need to worry. I will upload this revised version on Wattle. So any questions about dropping deviance test, about the previous lecture, about assignment 2? No questions, so let's continue, and we're going to start a quote new topic, because in this topic you will find a lot of similarities. And this topic is called the log linear regression model for Poisson counts. So basically we're still talking about the count data. In the previous lecture, we were talking about the binomial count. But here we are going to talk about Poisson count. So what's the difference between these two count data? And we will explain. And let's look at the outline. So still we are going to have a motivating example to help you understand why we need this new model. Because actually we have some new data, so we need to consider this new model. And then we are going to talk about the model. So usually when we talk about model, we talk about the model assumptions. So basically model assumptions define a model. And those assumptions are not necessarily satisfied for the real data. So we are going to have model diagnostics. And here we are going to have 3 tools. The first one is the log response versus explanatory variable plot. So if you still remember the multiple linear regression model, we have the response versus explanatory variable plot. So something similar here. And also we are going to have the Pearson residual plot. So in multiple linear regression model, we have the studentized residual plot. Studentized residual plot. So that is also something very similar. And the last one is the deviance goodness of fit test. We have mentioned it in the binomial logistic regression, and we're going to talk about that again in today's lecture. And you will find that the structure for this new topic is basically the same compared to the binomial logistic regression. So my suggestion for you to learn this topic is just to compare these two models and to know the similarities and difference. And in this case, I think this model is actually not hard to learn because there are a lot of similarities. And another thing is about what's the deviance goodness of fit test and what's the difference between this test and the dropping deviance test. So that is actually the last question asked in the previous lecture, so I will try my best to explain it again. So basically, these two tests are totally different. So the deviance goodness of fit test basically is used to test whether or not the model assumptions hold, or in other words, whether or not the model is good or is appropriate. So this is the deviance goodness of fit test. So in order to realize this, the test statistic is the deviance. So that's the deviance goodness of fit test. I think you have already seen it in the binomial logistic regression model, and we will talk about some similar tests for this Poisson log linear regression model. And for the dropping deviance test, so firstly, you need to know that we need to assume the model assumptions hold. So if the model assumptions do not hold, so we cannot use the dropping deviance test. So that's the first difference. The first difference here is that the deviance goodness of fit test is actually used to test the model assumptions, but the dropping deviance test is actually is used only when the assumptions hold. So if you have the deviance goodness of fit test and you reject the null hypothesis, so that means the assumptions do not hold. So in that case, you can never use dropping deviance test. So that's the first difference. So in this case, if the assumptions do not hold, you cannot use the dropping deviance test. But the assumptions, if those model assumptions are hold, or in other words, for instance, the deviance goodness of fit test is not rejected, so you may consider to use the dropping deviance test to test the following three. So these three are the special cases of the dropping deviance test. So the basic dropping deviance test is used to test several coefficients. For instance, beta 1 equals to beta 3 equals to 0. So it's one situation for the dropping deviance test. And another situation, which is called testing of overall significance. So even though it's called overall significance, but we can only do that when the assumptions hold. If those assumptions do not hold, we cannot do that. So this test is used to test all coefficients except for intercept equal to 0. So the only difference between the first and the second one here is that the second one actually tests a lot of coefficients. And the third one here is the testing a single coefficient equal to 0, which is basically equivalent to the Z test. So in the previous lecture, the student asked about what's the difference between the deviance goodness of fit test and testing of overall significance. So basically, they are totally different. So any more questions about the difference between the deviance goodness of fit test and also dropping deviance test? Any more questions? And if you see the difference, the way to compute the test statistic is also different. So the test statistic for the deviance goodness of fit test is exactly the deviance, but the test statistic for the dropping deviance test is the drop in deviance. So basically the difference of the deviance. So that's when we compute them, they are also different. Any questions? So if you still have any concerns about the difference between these two, do not need to worry, because I'm going to repeat it again by using the Poisson log linear regression model. So basically, they are totally different. Okay, so let's look at our motivating example. So in this motivating example, we are interested in modeling the car accidents in 41 counties in a country. So the response variable is the number of the car accidents for each county. So we have 41 counties, and in each county in the past year, we have the number of the car accidents. So this is the response variable. So you can see here we model the number, so that means we can call it the count response. And the explanatory variable here is the number of the traffic lights in each county. So that's our explanatory variable, x. So we are going to use the number of the traffic lights and also to model the number of the car accidents. So here, because we try to model the count response, so we need to consider to use the count modeling, but we only talk about the binomial count modeling. So let's firstly have a look at the data set. So this is the data set. So we have 41 counties. So obviously we can only show 30 counties. Sorry about it. We can only show 30 counties in this page, but we actually have 41 counties. And for each county, we have the number of lights, right? And also we have the number of the car accidents. So you can see, usually we have very small number of car accidents because I think the probability of a car accident is not very large. So that's kind of the feature of this kind of data set. So remember this feature. And then let's just try to use this similar terminology to help us to interpret the data. So here, we also have a trial, even though this kind of trial is, you can consider it as this is just some abstraction of the real case. So here, we can consider that we have a lot of cars pass through each county in this year. So each car passing through can be treated as a trial. So that's the meaning of a trial. And then we are going to have this success, even though it's not exactly the success. So one trial is called success if an car accident happens. When a car passes through this county, so this is the success. And the last one is the probability of success. So obviously here is the probability of an accident. So that's how we use these terminologies to help us to understand it. So if we look at these terminologies, these are exactly from the previous binomial logistic regression. So we actually have the number of success, which is the number of accidents. So we can denote it by using Z. Z is the number of success. And also we have the explanatory variable X. So a natural question, if you still remember the binomial logistic regression, the natural question is, well, is M? So what's M? M is the number of trials. So what's the number of trials? Because each trial means a car passing through, so the number of trials is actually the number of the cars that pass through the specific county. So the number of cars pass through each county. So here we do not have this in our data set. So here a very natural question here is that if we do not have M, how to model Z? How to model the number of car accidents? So that's a very natural question, because obviously for the binomial logistic regression model, we need to know the information of M. But here, we do not have this information in the data. So that's the question. So let's just try to summarize our question. So here, we should have the explanatory variable, the number of success, but in this kind of situation, we do not have the total number. We only have the first two. And Z is the number of success, which in our case is the number of the accidents, and M is the number of trials. In our case, is the number of the cars that pass through the county. And we have the probability pi. Pi is the number of success. So in our case, the probability of success, and this probability is the probability of an accident. And if you still remember in the previous lecture, in order to model this count response Z, we try to use this binomial distribution. So this is our binomial distribution. But the problem here is that the number of trials, which is the number of the total number of cars that pass through a county in this year, is not observable. So basically it's unknown. But we can imagine something. This M, which is the number of the cars that pass through a county, should be very large, right? Because we should have a lot of cars that pass through a county in a year. So in this case, we do not have the information, so how to model Z? So that's basically our motivation for this new model. So in order to explain how we model it, firstly, we need to introduce some new concept, which is called real events. So what's the real events? Remember, for the car accident, I mentioned something that the probability of a car accident is really small, right? So in this case, if we have this kind of situation, if the probability is of some event is really small, and we call this real event. So that means the event is not likely to happen. So this is the definition for the real event. And if we have this situation, if pi is very small, so that means it's a real event, and also M is very large. So in this case, we can define mu just equals to M times pi, so we can define this way. And we will find that this binomial distribution can actually be approximated by something different, by using this mu. So this is a very classical approximation, and you do not need to derive it by yourself. You just need to know that it's actually a conclusion. If we have the real events and also the number of the trials is very large, we are going to have this approximation to describe the distribution of count Z. So we can use the distribution on the right side, this distribution. to model Z, which is our count response, when we have this real event situation. And here, we call it Poisson approximation. So it has a name. We call it Poisson approximation. So why do we need this approximation? So obviously, in the binomial logistic regression model, we need to know n in order to model the count response Z. However, in this Poisson approximation, we no longer have m. So basically, m disappears in this expression. So what we need to know here is that if m is really large and also the probability is really small, so we are not going to have m in the expression of the distribution. So that's the advantage for this Poisson approximation. So in this case, we no longer need to use the information of n. So in that case, that might be helpful for us to solve the problem for the car accident data, because in the data we do not have n. So that's the way for us to solve this problem. So in order to understand it, you need to basically understand the binomial logistic regression model. So here, the only difference here is that we do not have n. So we consider to use something different to model this count response. So how can we model it? And we will talk about how to model it. So basically, this is the idea for us to model it. But let's look at the more, maybe more strict definition or more explanation or more interpretation for the Poisson count. So what's the Poisson count, Z? So basically, Poisson count Z is usually used for real data when we do not have m, do not have the number of the trials. So in this specific example, we know the number of success, which is the number of the car accident, which is denoted by Z, but we do not have the total number of the cars that pass through the county, denoted by M, so we do not have this information. But we know something is the total number of cars should be very large, and also the probability of a car accident is really small, so that's a real event. So in this case, if we have this kind of situation, we can call that a Poisson count. So if we have these two conditions, you can consider it satisfied. We will call a number or a count as the Poisson count. And obviously, no one will record the total number of cars that pass through a county. I think that's reasonable. So maybe you can imagine someone will record the total number of cars that pass through ANU, so no one will record that, right? But the police will record the total number of accidents. So that's usually the case. We record Z, but we do not record M. And in this case, I think we should have a lot of kind of similar situations for this total number of real events that occur over a given time, space, or volume. So in this case, we are going to have Poisson count. And we can give more examples of Poisson count. So in that case, you can understand it more clearly. So the first one is the number of the hospital admissions. So something similar to the number of car accidents. And another one is the number of kangaroos found over a particular area of land. So it's also, you can treat it as the real events to find a kangaroo, even though it's not that rare, I think, in Australia. And the last one is the number of the deaths by horse kicking. So it's really an absurd example, but it's actually the first example in statistics to use the Poisson approximation to describe the randomness of this kind of random variable. So basically, the Poisson approximation or Poisson count are used to describe the randomness of these real events. So in this case, we are going to propose something which is called the log linear regression for Poisson counts to deal with all the responses we have mentioned. So that's basically the motivation. And To this end, we still need to talk about something which is the difference between the counter response and also the ordinal response, if you still remember the ordinal response. So for the counter response, I use this example 4. So if you still remember the previous, I think the lecture for the multi-category response, we have example 1, which is the binary response, and example 2, which is the nominal response, and example 3, which is the ordinal response. So here we have the counter response. So counter response can take this value once, twice, 3 times, and so on and so forth. And here we can define 1, 2, 3 to represent this counter response. And also obviously we have order. So that's the similarity compared to the ordinal response. But the huge difference between this counter response and ordinal response here is that the difference of count, for instance, 2 minus 1 and 3 minus 2, they actually have meaning. So it's totally different. So this part is different from the ordinal response. So basically, the ordinal response do not have this kind of property. So that's the difference between the counter response and also the ordinal response. So that is the difference in the counter response actually has some meaning. So in this case, we cannot use the ordinal response regression to fit the data because the ordinal response regression model does not have this meaning for the difference. So that's the difference between the counter response and the ordinal response. Any questions for that? Okay, so I think we are well prepared for the Poisson log linear regression model. So it's actually the last model we're going to talk about in this course, so which is the last generalized linear model. And compared to the previous models, you can find a lot of similarities. So basically, we have a slightly different response variable, so we need to propose a new model. But for this new model, we can still use some continuous and categorical explanatory variable to model this new kind of response. So that's something similar. So what is this model? So let's look at the model assumptions. So you can compare these model assumptions to the binomial logistic regression model assumptions, and you can find some similarities. And in this case, we still model the response variable given some value of the explanatory variable. And in this case, if we consider the explanatory variables are given, and then we model the probability of the count z equals to the lowercase z given x is defined in this way. So if you still remember, this is the Poisson approximation. So in this case, by using this distribution, we no longer have the m, we only have mu. And z can be 0, 1, 2, 3, 4, 5, because the number, if you still remember, the number of cars that pass through the county is really large. So here, the number of car accidents can also be large. But usually it's not that large, but it is possible that it's large, maybe with a not very large probability. And here, we just call this distribution Poisson distribution, if the probability can be derived in this way. So let's look at what's the meaning for mu. So if you compute the mean of response, so how to compute the mean of response in this way? Because here, obviously z is a discrete random variable. And if you still remember how to compute the expectation or the mean of a discrete random variable, so usually when we have the distribution in this way, so this probability here describe the distribution. With the distribution in this way, then the mean can be computed by using 0, because z can be from 0. 0 times the probability of z equal to 0, plus 1 times the probability z equals to 1, plus so on and so forth, maybe just plus 2, and z equals to 2, and plus so on and so forth, and we can compute, I think, in this way. So that's how we compute a discrete random variable. And you will find that if you compute in this way, and that should be in your 7055 course or 1008 course. So you will find that the mean of response here, if you plug in the expression of the probability, just plug in the expression here, here, and here, and based on some calculus, obviously it's not required in this course. So based on some calculus, you will obtain this conclusion that the mean of response is exactly equal to mu. So what's mu? Mu is actually some parameter in the expression of this distribution. So usually for a Poisson distribution, we usually use Poisson mu to represent a Poisson distribution, and mu is the, you can consider it as the mean parameter of this Poisson distribution. And the mu actually has a meaning, so it means the mean of response. So that's the property for the Poisson distribution. And since we have this kind of distribution to model our response variable z, so the second part is, if you still remember the basic idea in the statistical modeling. So if we have something unknown, we just model it. So that's basically the idea. So if you remember the multiple linear regression model, we have no idea about the mean of response. So we model the mean of response as a linear combination of the explanatory variable, remember? And in the binary logistic regression model, we have no idea about the probability of the response equals to 1. So we model the probability of the response equal to 1. And in the multi-category response regression model, we have no idea about what's the probability of each category. So we model the probability of each category as some function of the explanatory variable. And in the binomial logistic regression model, we have no idea about the probability of success. So we model the probability of success as some function of the explanatory variable. And finally, we have our last model. We have no idea about mu, so we model mu. So that's the logic. So consistent logic for the statistical modeling. If we have no information, we do not know something, just model it. So how to do that? So firstly, you need to be very careful here because this mu parameter is larger than 0. So in this case, we need to consider the generalized linear modeling idea. So what's the generalized linear modeling idea? So the idea here is just to match the range of two things on the different sides of equations. So obviously, the linear combination here, the range is from minus infinity to infinity, right? But the range of mu here is from 0 to infinity. So the range, these two ranges do not match. So that's the problem. So in order to make sure that these two can match, so we need to introduce some link function. So that's the basic idea of generalized linear model. So we can use this one sentence to summarize all the generalized linear model, basically to match the two sides of the equation, the range of the two sides of the equation. So in this case, we consider this link function as the log link function. So it's a new link function compared to the previous modeling. I think if you still remember, all the previous generalized linear modeling use the logit link function instead of the log link function. So this is the new link function. So by using this new link function, we can make sure that the left side and also the right side of the equation can have a match for the range for the two ranges. So that's the idea. So we model the transformation of the mean of response as a linear combination of the explanatory variables. So that's the generalized linearity. And also, you can consider the transformation because the log of mu equals to the linear combination. So mu just equals to the exponential of the linear combination. So this is equivalent. And if you have a look at it, the mean here is from 0 to infinity, and the exponential of something also is from 0 to infinity. So in this case, we have a match for both sides of the equation. So let's try to use some display to show these model assumptions. So what's the model assumptions, if you still remember? So the model assumptions, the first one is the Poisson distribution. Poisson distribution just means that if we given some value of x, for instance here, we're given x equals to 5, we have a Poisson distribution. And also given x equals to 15, I think here, we also have a Poisson distribution. And given x equals to 20, we have another Poisson distribution. So you can find that given different value of different x, we have a different Poisson distribution. So here, basically, we have the Poisson distribution. So here we have a Poisson distribution with the parameter here, which is the mu y given x equals to 5. So this is the Poisson distribution given x equal to 5. And also here we have a Poisson distribution of the parameter y given x equals to 20. When x is different, the mean of response is also different in the modeling. And in this case, we are going to have a different Poisson distribution. So this is the first assumption. And the second assumption here is that the mean of response, so maybe I need to use Z, sorry. I think to keep consistent, I need to use Z, sorry about it. So that's the first assumption. And the second assumption here is that the mean of response is an exponential function of the explanatory variable. So that's our second assumption. So you can see this straight line. So here, for each Poisson distribution, we can compute the mean of response. So these are the mean of response. This is the mu z given x equals to 5, and this is the mu zx equals to 20. For each explanatory variable, we can compute the mean of response. And if we consider the regression line for all this mean of response, we can find that it's actually an exponential function of the explanatory variable. So this nonlinear and increasing curve just means the exponential of x. Exponential function of x. So that's the model assumptions. The Poisson distribution, and the second one is the mean of response is actually an exponential function of the explanatory variable. So that's these two assumptions. And the third assumption is always the independence assumption. We assume all the observations are independent. So we have the observations of x, and also we have the observations of z, and we have m as our sample size. So we just keep it consistent with the binomial logistic regression model, because obviously this two has some kind of similarities. So what's the sample size for the car accident example, if you still remember? Because we have the number of the traffic lights and also the number of the accidents for 41 counties. So in this case, we have Z1, Z2 until Z41. Because we have for the number of the car accidents for 41 counties, so the sample size M equals to 41. So you need to know that how to get the sample size. So usually we can use the length function to obtain the sample size, and I think you should use the length function a lot in your assignments. So that's these three assumptions to describe this Poisson log linear regression model. Any questions? So these assumptions are really important to define this Poisson log linear regression model. If you do not have any questions, so that means you have understood this log linear regression model. So then, based on these assumptions, so let's try to look at the interpretation of the coefficient in the modeling. So if you look at the model, so the most important feature for the model here is the mean of response is modeled as an exponential function of the explanatory variable. So you can actually compute the mean of response given x equals to x plus 1, and the other x's are equal to x2 to xk. So the first one, you can compute this mean of response, and here is the result. And also, you can keep the other variables constant, but revise this x1, and you can obtain another mean of response. So if you compare the difference between this mean of response, you can find that the only difference here is the exponential of beta 1. So what's the meaning for this exponential of beta 1? So the meaning is here, something similar to the interpretation of odds. So here, we consider if x1 is increased by 1 unit, then the mean of response will change by a multiplicative factor of exponential of beta 1. So here we consider it as change, so it does not necessarily increase, but it is a change by this multiplicative factor. And here we also give some more interpretations of it, but this interpretation is only valid when beta 1 is small. So this is some new interpretation, but it's only valid when beta 1 is small. So if beta 1 is small, we will have this kind of approximation. It's actually you can consider it as the exponential approximation, or if you have learned some calculus, it's also the Taylor expansion approximation, but it's totally fine. So what we need to know here is to understand this example. So you can have a try in your R or in your calculator. The exponential of 0.05 is approximately equal to 1 plus 0.05. So in this case, we will have beta 1 here, and also beta 1 can be approximately be 0.0513. So this is only valid when beta 1 is small, but when beta 1 is large, like 0.5, so it's no longer valid. So you can only have this interpretation when beta 1 is small. So if beta 1 is small, so originally we should have mu z given x plus 1 equals to the exponential beta 1 of mu z given x1. So that's our original situation. The difference is this multiplicative factor. But if beta 1 is small, we can replace it with this 1 plus beta 1. So what's the meaning here? So it's kind of more straightforward compared to the exponential of beta 1. So in this case, because we have this kind of approximation, so if beta 1 is small, so we can interpret beta 1 as the percentage increase in the mean of response for 1 unit increase in x1. So why it's percentage increase? So let's just have a look at it. For instance, we can also use beta 1 equals to 5%, so that means 0.05. So in this case, this approximation just equal to 1 plus 5% times the mu z given x1. So in this case, this 5% can be interpreted as the percentage increase in the mean of response if we increase the x1 by using by 1 unit. So this percentage increase interpretation can only be used when beta 1 is small. So that's something new, but the multiplicative factor interpretation is exactly the same compared to the binary logistic regression model, binomial regression model, and also the ordinary regression model. So this multiplicative factor interpretation is the same. Any questions about the interpretation? Okay, so let's just look at how to fit the model based on the data set. And obviously, if we have defined the distribution of Z, and also we have the independence assumption, we can actually compute the probability that we observe Z1 to Zm. So we can compute the probability of that we observe Z1 to Zn. So by using it, we can define the likelihood function. And because the likelihood function is exactly equal to this probability, and because the probability of each Z, if you still remember here, the probability of each Z depends on the parameters mu, and the mu depends on beta 0, beta 1 until beta k. So this probability depends on beta 0, beta 1 until beta k. So this is our likelihood function. So by using assumptions, we can obtain the likelihood function, and I will not derive in this course because it's beyond the scope of this course. But what you need to know here, we can obtain the likelihood function by using the assumptions. And for the generalized linear model, if we can obtain the likelihood function, we can maximize this likelihood function and obtain the maximum likelihood estimation. So that is our estimates. And if we can get the maximum likelihood estimation, we can use everything in the inferential tools for generalized linear model. I think that's in one of the previous topics. So in this specific modeling, so what you need to do here is just to input the response variable Z, which is the number of accidents, and also the explanatory variable, which is the number of the traffic lights in the modeling. And then you need to specify here, because we are using the Poisson log linear model, so we need to specify Poisson distribution and also the link function, which is log. So that's the difference between this model and the binomial logistic regression model. And the next step is just to look at the summary output. And actually, this summary output is similar. So you will have the maximum likelihood estimation here. And also, we have the standard error here. And also, we have the Z value. So the Z value is the test statistic, which is beta j hat divided by the standard error of beta j hat. And this is the test statistic of the hypothesis beta j equal to 0, which is our standard Z test. And the p-value is the corresponding p-value. And by using this p-value, we can find that, obviously, the number of the traffic light can be used to predict the number of the car accidents for different counties. So that's the p-value. And also, by using the estimate and also the standard error, we can obtain the 95% confidence interval is the beta j hat minus plus 1.96 times the standard error of the beta j hat. And 1.96 is actually the 97.5% quantile, which can be represented by using 0.25. So this is the 97.5% quantile of the standard normal distribution. I think everything here is standard, right? And also, in the table, we have the non-deviance, we have the residual deviance. So the residual deviance is the deviance of the model. So the model here is the car accidents point Poisson. So this is our model. So our model here is the model with Z and also the explanatory variable X. And also we have the non-deviance. Non-deviance is the deviance with intercept only. That's also the same compared to the generalized linear model. And by using these two deviances, we can actually construct the testing of overall significance, if you still remember. So we can use these two to construct test of overall significance. So how to construct this test? In this page. Because we only have one coefficient, we only have one explanatory variable, so that means we only have the, except for the intercept, we only have one coefficient, which is beta 1. But this test is exactly the test thinking of overall significance in this case. And I think that's the end of today's lecture.